Today I'm going to be talking about experiment 16 and 17, qualitative analysis of the group 3 ions. So some of this that I'm going to discuss, we started discussing when we talked about qualitative analysis of the group 2 ions. So on the screen is table 1 from the qualitative analysis of group 2, and it has so that's experiment 13 and 14, and it has values for the KSP for different group 2 ionic solids with sulfide. So here I circled copper sulfide in the KSP. Here I circled nickel sulfide in the KSP. So these are from the two different groups, and they have the same number of ions, so we can compare the KSPs. And we see that the KSP for copper sulfide is very, very small. The group 2 sulfides are very insoluble. Right, so nickel sulfide has a very small KSP as well, but it's not as small as what we see for copper sulfide. So they're insoluble, but they are more soluble than group 2. So just like we discussed in group 2, we can control the concentration of sulfide by controlling the pH of the solution. So we're going to look at next that reaction. So we have the H2S on the left forming S2- on the right, our acid dissociation reaction. So I want to ask you, what happens to the concentration of hydronium when we increase the pH? So go ahead and write down your answer. Hopefully you said that we decrease the concentration of hydronium when we increase the pH. So the concentration of hydronium goes down. So now, according to Le Chatelier's principle, which way will the reaction shift? Write down your answer. It shifts to the right. Okay, so shifts to the right. So what happens to the concentration of sulfide? The concentration of sulfide increases. So overall, that means at a higher pH, we have a greater concentration of sulfide, and we will precipitate out the more soluble group 3 ions. And to get the correct pH, we will use an ammonium-ammonia buffer system. That's going to give us the proper pH to precipitate just the group 3 ions. So we're going to look at our flow chart here. Our group 3 ions are nickel 2, cobalt, iron 3, aluminum, and zinc. And so we're going to start, if we were doing the experiment, with 5 mils, and we're going to heat gently to get 2 mils to concentrate the ions. And then we would add our buffer system, the ammonium and ammonia buffer. And that creates some hydroxide precipitates, but then we add thioacetamide, which gives us our sulfide. And overall, we get a precipitate with our group 3 sulfide, and as well as though aluminum actually precipitates with the hydroxide from the buffer by increasing the pH. So adding 6 molar HCl will separate precipitate and supernatant. It's difficult to separate, just like in group 2, so we have to use a Pasteur pipette to suck out the supernatant, which we would set aside for later tests. Let's focus now on the precipitate, which contains cobalt sulfide and nickel sulfide solid. And at this point, we would add aqua regia, which is 12 molar HCl and 6 molar nitric acid to dissolve this precipitate. And this will give us complex ions with chloride as the ligand with cobalt and nickel. Then we would go ahead and separate to test for, first let's test for cobalt. So we take 1/3 of the solution and we would add ammonium thiocyanate. And this gives us a very pretty blue color solution if we have cobalt. There is another test for cobalt. It is less sensitive, so we usually don't worry about it too much. We'll usually get a positive test for 4A and not really do step 4C. To test for nickel, we would take some of the solution and we would add DMG. And that gives us a rose red or pink colored solid, which actually will stick to the sides of your tube, if you can see there in that picture. That's my favorite colored precipitate that we get. So focusing on the other side of the flow chart, here we have some ions in the supernatant, and you'll see nickel there as well. So some nickel may be present. So we actually have to do tests for nickel twice, and we got to get at least one positive to say that nickel is present. So we're going to go ahead and add our reagents, and that will give us some hydroxide precipitate of iron 3 and nickel. And we can dissolve that. And then we can add some potassium thiocyanate to test for iron, and it should give us a blood red solution. Okay, so this gives us a blood red solution to show that iron is present. So we would want to, if we had a negative test in step 5, we'd want to test for nickel again. Okay, so testing for nickel again would give us that rose red precipitate. So we don't have to do the centrifuging and testing for nickel if step 5 was positive. But if we had a negative for step 5, we would definitely want to do this. Okay, so if step 5 was negative, we would do this test for nickel over on this side of the flowchart. So we need one positive nickel test. So if we get a negative in step 5, we'd want to do the step here, step 8B and step 9. If you do have to do steps 8B and 9, you would also see a rust red precipitate of iron hydroxide. Okay, so going back to the supernatant from step 6, we have some complex ions of aluminum with hydroxide ligands and zinc with hydroxide ligands. We can go ahead and make that just basic and get an aluminum hydroxide precipitate. We want to look very carefully. It looks gelatinous. It's kind of hard to see, so that is not for sure our positive test for aluminum. We would add acetic acid and this substance called catechol violet and get a blue complex for a positive aluminum test. Here for zinc, we would have a complex ion from step 10 with ammonia as our ligands. And then we would make it acidic and add a complex ion salt to give us this complex ion solid, which may look gray, but usually it looks pretty green like we have in this figure here.